7.3 Translation Theorems and Derivatives of a Transform. What do we have here? Well, what is this? There are two parts in this section. Two parts to this section. The first part talks about, if you remember how we did we found the Laplace transform from before. Do you remember from section 7.1, when we started Laplace transform, the first thing we talked about in Laplace transform is the definition of Laplace. So recall, we defined Laplace of f of t is the integral 0 to infinity e negative st times f of t dt for t bigger than or equal to 0. Right? This is called the Laplace transform of f of t. That was the Laplace transform. But imagine when we did more examples on this in that section, like the later examples, we found out that they can get more difficult actually to integrate improper integral like this by doing, like, especially if you go through by integration by parts or something more difficult than that. It will make things more difficult for you to do integrals and spend a lot of time integrating. So this section, the first section, to make things easier for us to find Laplace transform. So to make things easier for us, we use translation or shifting, shifting a function from right, left, left, right. Fs, the Laplace transform, using f of s minus a. So if a is positive here, then this means you're translating f of s a units to the right side, if you remember that from algebra. This is called the first translation theorem, or first shifting theorem. And since we call the first translation theorem or first shifting theorem, this means there's another one, right? There's a second one. So if for any a real number, so that's a real number, if a is any real number, then the Laplace of e to the at times f of t, we're going to define it by f of s minus a. So what is f of s minus a? Where capital F of s is the Laplace of small f of t. Laplace of small f of t. So note, we can write the Laplace of e to the at times f of t. You can write it is the same as the Laplace of f of t by replacing s with s minus a. So you find that the Laplace transform of f of t and replace s with s minus a. Evaluate, to apply this so you can see it, evaluate the Laplace of e to the 3t times t to the 4th. So let's look at this one step at a time. What is going on here? So if I compare these together, that tells me f of t is, you can write here on the side, f of t is t to the 4th. That's the first thing. And from this number here, that's the a is 3. These are the things that you need. And notice what we said in the line right above it. We said, hey, you can just simply find the Laplace of this function here. We can simply find the Laplace of f of t, which is t to the 4th, and then replacing s with s minus a. A is 3. Okay, so hopefully this looks good. So now how we finish this up? The Laplace of t to the fourth is 4 factorial over s to the 4 plus 1, 5, right? Replacing s with s minus 3. So 4 factorial is 24, and now we're going to replace s with s minus 3 to the 5th power. So that's the Laplace of that. And you say, wait, why do we have to do it this way? Well, if you want to do it using the definition of Laplace, the one that I introduced at the beginning of today's lesson, I recall from before, then what is going to happen here, you're going to find that you have to use integration by parts. Not only that, but probably you have to use it several times to be able to solve this. Maybe like 3 or 4 times. Imagine how much work is going to be put into this to be able to find the Laplace transform for something like this using the definition of Laplace. By using the shifting theorem or the first shifting theorem, it makes things much easier. So another one, find or evaluate the Laplace of e to the negative t times cosine 4t. We can go over it now. So the first thing I would say, what is the function f of t? F of t is cosine 4t. I like to list them out. And a here is negative 2, this number there. That's a. So this is the same as the Laplace of cosine 4t, replacing s with s minus a. So minus minus is plus 2. And what's the Laplace of 4t? The Laplace of 4t is always s squared, plus the 4 that you see there square. Replacing s with s plus 2. That would give me, replace s with s plus 2, you get s plus 2 square plus 16. Done. Much easier than what we learned in section 1. Now, can we do inverse for that? So inverse form, is there an inverse form? Yes, there's an inverse form of the first translation theorem, which says that the inverse Laplace of f of s minus a, backwards, is the inverse Laplace of f of s, where s get replaced with s minus a, and that would equal e to the at times f of t. Kind of like backwards for what we just did. What is f of t? So f of t is inverse Laplace of f of s, capital F of s. And how is that being applied? Let's say we are asked to evaluate inverse Laplace of s over s squared plus 4s plus 7, like so. The first thing we need to do here is, this does not look like any of the function. It doesn't look like cosine or sine or anything like that, because the denominator is non-factorable. You can't break it down. Or what can we do then? Well, the only thing to do here is to look at the denominator and complete the square here. Complete the square by adding 4 and subtracting 4. So that becomes s plus 2 squared plus 3. That's for the denominator. So now we need to find the inverse Laplace of s over s plus 2 squared plus 3. And to make these things work, so it's kind of more tricky than the one we just did earlier, because you're going backwards. You have to think backwards about this. What happens is, if I go back up, let me scroll back up. Notice when I did this last one, what we got. If there was an s plus 2, there's an s plus 2. They match, because what we did, we replaced the s, each s with s plus 2. So if you have s plus 1 squared down here, you should have s plus 1 on the top. S plus 3 squared, you should have s plus 3 on the top. And the same thing, it might happen in the case of cosine every time. Here we don't have s minus 3 because this is for sine. Or like there's no, actually, sorry, for exponential. And same thing works for sine. But in case of cosine, you have to have these numbers or these terms match, s plus 2, s plus 2. So I see here s on the top. So when s on the top, that reminds me of cosine. So then they have to match. So how does that match? Well, how do I make that match? Well, one way to do so is you add s to make it match, but then you subtract 2. So you add 2 and you subtract 2. Okay? So then what we can do, by the linearity of Laplace, inverse Laplace, we can split this into 2 Laplace informations. So that 2 comes outside, Laplace inverse of 1 over s plus 2 squared plus 3. Notice the second one doesn't have s on the top, so I don't care about if they match or not. But as long as there's a 1 there, it's fine. Now on the left hand side, it's kind of backwards. You can go backwards to what we did before. So what I'm gonna do, notice, let me go back to the previous example. So what was the step before the final step? Well, there was an s, like kind of, if you want to go backwards, you subtract 2 here, right? You subtract 2 backwards. And then from the backwards, you got to the function, the cosine, or the Laplace of that function. So what I can do here, because there's an s plus 2, we can rewrite this Laplace inverse of s over s squared plus 3, okay? S plus 3, and then you can put it inside or outside, doesn't matter, by rewriting it backwards as if I'm gonna replace s with s plus 2. Minus, keep the 2 there, Laplace inverse of, let's say here what we do, again, s is gonna be replaced with s plus 2, and this is gonna become s, and this is 3. Now the 3, remember I need it to be square, so I can put a square there, and I put a square here, square root of 3 square. In the sign, they have to match. This number here I'm highlighting must match the number on the top. So I have to have square root of 3 there. And we do the same thing outside to balance that expression. So then what happens here? How do I come out of this? So it's ready to work backwards. If you remember, let me go back up. So I'm going backwards. So when we got to that point and went back, what was in there was exponential function and cosine, right? It's exponential and cosine. So this is the this can be written as e to the negative a. What is a? A is negative 2 t cosine whatever that number there, t, minus 2 over the square root of 3. This is again the same thing, e negative negative 2t. So the 2 is coming, this 2 is coming, or negative 2 is coming from here, and the same thing there, that's where this is coming from. And then this is sine radical 3t. This is radical 3 or square 3 is coming from this one. Same for another example. Evaluate inverse Laplace of 1 over s minus 1 to the 4th power. How do we find that out? To start with this one, the first thing is this is Laplace inverse. Let's see what we have. S minus 1 to the 4th. Just imagine that this is s to the 4th in that sense. So what goes on the top is the 1 less than the exponent factorial. So if it's 4, it goes 3 minus 1 factorial. And since we put a 3 factorial there, we have to multiply by the reciprocal outside. So the next step is, this is 1 over 6 Laplace inverse of 3 factorial over, rewrite it as s to the 4th, where s get replaced with s minus 1. That's the a value. Okay, you can write it this way, or just so you know, if you see something somewhere else like this, you can write 3 factorial s to the 4th with a bar like this, as replaced with s minus 1 and braces. So then This is 1 over 6. This reminds us of e to the, remember a is 1, at, so 1t times t to the third power, because this is always one more. So that would be the inverse Laplace. How about another example? Find inverse Laplace of 1 over s squared plus 4s. So what do we do with this? Inverse Laplace. As you can see, you can factor s out, but then s times s plus 4, you can do partial fraction decomposition, but in this case, I think we should do completing the square. So on the side, s squared plus 4s, you can add and subtract 4. So that becomes s plus 2 squared minus 4. So that goes as s plus 2 squared minus 4. So then, think about what the next step should be. Okay, so the next step, I want to make the s plus 2 squared as s squared minus 4. So 4 means 2 squared. So I have to have 2 on the top. And because I put a 2, I have to put a 1/2 in the front. And then remember, s goes to what? S plus 2 backwards. Replace with s plus 2. So 1/2 e. A here is -2, so -2t, and this one here inside, this is the hyperbolic sign of 2t. So this 2 is coming from this 2. That's the 2 for this one. Again, you could have done this using partial fraction decomposition, but there will be more work involved, and it's guaranteed you're going to get the same answer.